All right, so I wanted to give you guys a little help on the homework. The night problems from chapter 8. I think the assignment is to do problems 7, 9, 11, 13, and 15. The nice part about this is all the answers are in the back of the book, but it still doesn't mean that it's not tricky. So some of the problems are tough to start. And so I'll give you a little bit of help here, and hopefully it heads off some of those problems. All right, so let's look at number 7. 7, I think it says there's a rod with a pin. So let's go ahead and draw that. And there's a pin right here at the end. It says, how much torque must the pin exert to keep the rod in figure 8.7 from rotating? So that means it's going to be in equilibrium, right? Calculate this torque about an axis that passes through the point where the pin enters the rod and is perpendicular to the plane. So that point would be right here. And it's going to be into the page, right? And so this is going to be our pivot. This red dot right here. Okay. What else is true here? Looks like we got a 2 kilogram rod. And I kind of want to write that off to the side because I think I'm going to end up having a center of mass here, symmetrical object. And so we're going to have a force gravity of the rod, which is going to exert a torque. And we're also going to have a torque from this weight at the end. Right? And this is also going to exert a force, albeit a smaller one. And we'll say this is Fg, what do you want to call this? Mass? We'll call it Fg mass. And they tell us that this mass is, I think it's 0.5 kilograms. And this rod has a mass of 2 kilograms. Okay, so we got 2 forces acting on this pivot. So, and both of them point this direction here, right? They're going to torque this way. And this kind of torque is negative torque, right? So we're going to have a counterclockwise torque, but it's in equilibrium. So therefore, this pin has to exert a force the other direction. And so right here, there's some kind of force from this pin that counteracts this. You might say, well, why is it not at the red dot? Well, if it was at the red dot, then it wouldn't exert any torque because it would be at the pivot. So that would be a problem. So it's actually going to be right there, and it's going to point upwards to counteract this torque, right? Because we need a torque about this axis that's going to go this direction. And this is going to be clockwise torque. This is going to be positive torque, right? And so that's going to balance it out. You don't even have to actually start this problem with balancing the y forces, although you can. So you could actually find the force of the pin if you wanted to. But what you're going to want to do, or the easiest way through this problem, is go right to sum of the torques and set it equal to 0. And even though we don't know this distance right here, right, from the axis to the force of the pin, where that yellow mark is right there, we don't know that distance, right? This distance right here, it's a mystery. We don't need to know it. We're just interested in the torque. So I guess if we had the force pin and we had that distance, we could find the torque. But I think from this torque balance right here that we're going to do, we can actually just calculate the torque from that. All right, so that should help with problem 7. Let me go ahead and add another page. Well, I guess I already have one. Maybe this is enough pages. Let's go ahead and draw a line there. And let's go to problem number 11. All right, 11 has something like this. There's actually a picture in the book for this. It's kind of a weird looking, it's got like a couple blocks on a fulcrum. And it looks like, let's see. Okay, so this block, so this is going to be a 2-meter long object. And this block on top of it is going to be 1 meter long. So we got 2 blocks resting on top of a fulcrum. And they tell us that it is balanced on the pivot. So when they say balanced on the pivot, I think they mean balanced on this fulcrum. So they're saying, yeah, balanced right here is what they're saying. So I'll just write balanced. And this distance right here is 1 meter. Okay, then they tell us that this mass right here is 4 kilograms. And the mass underneath it is 2 kilograms. And then they ask us, do I have that right? No, 1 kilogram. I'm sorry. Let's fix that. 1 kilogram. Then they ask us, what is this distance to the pivot or the fulcrum? They just call this D. Now, what I'm going to say here, and the reason I didn't write pivot down, is because I want to actually move this pivot. I want to move it away from where it is. I think this problem is easier to calculate if we move the pivot. So what I'm saying here then is we're going to let's draw some forces first, so we're clear on that. I think on this the forces on this object in the middle, right? We know that on this middle object, there's going to be a force gravity acting at center mass. So I'm going to call this FG1. And I am not drawing this to scale, right? Obviously, FG1 is going to be much smaller than the FG4. I'll try and draw it a little smaller. I'll give it another shot, because I should draw it smaller. All right, and that's going to be FG1. Let me erase this. Okay, and then we have FG4, which is going to act from its center of mass. So right here, and this one's going to be obviously 4 times as great. It's kind of hard to see. Hopefully you can see what I'm trying to draw, that symbol. Let me see if I can fix it up a little bit. All right, something like that, right? And I don't know the distance from either of these forces to the fulcrum or the pivot. And so that's a problem. Okay, so we also know that at the fulcrum or the pivot, there's one final force that's going to point up, and that's going to be the normal force. That's going to act on that middle object, right, from that point of the fulcrum. So we know this is going to be a large enough force to balance out FG1 and FG4. So I'm going to draw it a little larger, and we'll call this force normal. So what we're going to end up doing here is this is going to be two steps, right? First step is going to be to find Fn. We'll do that. So step one, find Fn by balancing the y forces. So I'm just going to sum my y forces and set them equal to 0. So I'll let you do that. And then step two is going to be, go ahead and write this down. Step two, we're going to balance the torques. Now, the problem with balancing the torques is that we don't know either distance FG1 and FG4 is from the natural pivot there. Force normal is not a problem because it acts through the pivot. So to deal with this, let's just move the pivot, right? The pivot doesn't have to stay there. That's what's amazing about these equilibrium problems. We can put the pivot wherever we want. So let's put the pivot, since we want to know the distance that this force normal is acting from the left edge, let's put the pivot at the left edge. So now, when you solve your torques, right, your R values are going to be here to the old pivot here, and then finally to this R value will be right here. And what are those R values? I think you can solve them. I think because of the geometry is not too difficult to deal with. You know that the total length here is 2 meters, right? And you know that the total length of this shape is 1 meter. I think you can figure out those R values, except for D, obviously, because D is what you're solving for. But I think the R values of FG1 and FG4 are obvious from the geometry there of the shapes. So I'll let you, and in knowing where the center of mass has to be on a symmetrical shape, right, in the center. Okay, so the next step is find D by balancing the torques. About the new pivot. And I'll just write in parentheses red, because that's where the new pivot is. Okay, let's go to the next one. Next one I want to help with is 13. So 13 is tricky because it's not intuitive. There's a person on a diving board, and there are 2 fulcrums here, and there's a hinge right here. The other fulcrum is right here. And the distance from fulcrum to fulcrum, they tell us, is 1.5 meters, which is half the board. I just can't draw. So let's see if I can fix that. Maybe I can. Let's erase this guy. Oh, let's just erase the whole board. Why not? Okay. So the board itself is going to be 3 meters long. So maybe about right there. Right? Yeah. Okay, so the board itself is 3 meters long. You think with all these straight lines, it would help me draw this, but it really, I'm still struggling. Okay, so we have something like that. And this is 3 meters. Okay, so why is this a problem? Well, let's draw the person again. All right, forces here, right? Let's go ahead and label some of them. We got the force gravity of the board itself, right? It tells us it's a 30 kilogram board. So that's going to act at the center of mass, which is right in the middle, which is actually where this fulcrum is, because it's 1.5 meters from the left. So there's the force gravity of the board. We have the force gravity of the person. I'm just going to go ahead and draw it acting on the board right here. I'm not sure if the person's more massive. Oh yeah, 60 kilograms. So I'm going to draw a straighter or a longer line. Thought I'd get a straight line there. I guess not. All right, force gravity person. All right, good. Good. So far, so good. This is a 60 kilogram person, by the way. And this is a 30 kilogram board. Okay. And then finally, we have force normal. Let me go a different color here. And it's going to act at this middle fulcrum and point up. What is this force normal, or how large should I draw it? I don't really know. I'm just going to go ahead and draw force like that. Okay. Good. All right. So we run into some problems here unsuspectingly. I think the question is, what is the magnitude of the vertical force exerted by the hinge on the board? And it'd be really easy just to draw another purple force and point it up, right? It seems like it makes a lot of sense. But we don't know anything about force normal. And we would have two mystery forces at two different force normal mystery forces. And that's a huge problem. We could balance the y forces and not get too far. We could then try and balance the torques. Would that work? Well, we still wouldn't know the middle force normal force. And we also run into problems because we don't know what this y force is doing. Meaning, is the force at the hinge actually pointing up? And so an easier way to solve this problem, since we don't know anything about this force at the hinge, let's do this. And this is like a little bit of a trick here, right? Let's eliminate this force in the middle. How are we going to eliminate the force in the middle? Well, we can't just eliminate it. How do we get it out of a torque balance, though? Let's put the pivot there. So this green dot I'm drawing is going to be my pivot. Let me try and put some black there too so it's easier to see. That green dot is the pivot. Okay, so if we do that, then force gravity board and force normal exert no torques. However, force gravity of the person exerts a torque this direction, which is negative torque. And therefore, we need a positive torque to balance this out, right? So positive torques point counterclockwise. So which direction does the force at the hinge have to point to have a counterbalancing torque? Think about that. Well, to have a counterbalancing torque, the force at the hinge has to point down. And this is why, if you would have did it the most natural way, right, with keeping the pivot at the hinge, you probably would get the wrong answer because I'm guessing almost 100% here, that you would have pointed that force up when you balanced the y forces, and that would have been technically wrong. So this is the force of the hinge, or at the hinge, that it exerts on the board. So the question is, what is the magnitude of the vertical force? They don't even tell you it's pointed down, right? They just call it a vertical force, right? And but this hinge force will now give you the positive torque you need. So you do not have to sum the y forces. I would go right to balancing the torques. And I would do it with these two forces, force hinge and force gravity person, both giving you a torque, and then solving for the magnitude of the force hinge. So just go ahead and sum your torques, set it equal to 0, and you should be on your way to getting the right answer. All right. Hopefully that helps get you started, and it's helping make those problems a little bit easier. And yeah, let me know if there's any questions. If you can't get through them all, that's fine. 15 looks a little challenging. I guess on 15, you might have some X forces, and you might also want to balance your X forces, and also consider breaking tension down. So on 15, it might be something like this for the diagram. I haven't read the problem recently, but I have my notes here, and I'm just looking at it, and I know it's going to cause some headaches if I don't say something. So I think on 15, you have something like this. I think you have a bar here with some kind of mass, so there is a center of mass, and there's going to be a, let me just check up here. Yeah, it's a 10 kilogram beam, so there is going to be some kind of force gravity from the beam. It looks like it's free to pivot right here. I'm just going to go ahead and call that the pivot. I'm not sure if we'll keep it there or not, but yeah, that's what they want us to think about. We have a string or a rope attached to the end of the beam. This is going to give us a tension force. We know our tension forces always pull. So this is going to point this direction right here, and we'll call that T. We can split that up though, all right? We don't like forces that point weird directions, into a Ty and a Tx, all right, like that. Make a 90-degree angle right there. Let me erase that one T in the middle, it's just kind of floating around. Try and write that closer to here. What else do we know? I think we have to end up, it says here, a uniform beam of length 1 meter and mass 10 kilograms attached to the wall by cable, shown in the figure. Beam is free to pivot at the point where it attaches to the wall. What is the tension in the cable? So we got to solve for tension in the cable. We do know, though, that the wall has to exert a normal force here, right? There has to be a force normal from the wall because to balance out Tx. Right, there has to be that there. Does the wall exert an upwards force? Yeah, it does have to do that. And why is that? I don't even know if they ask you about it, to be honest. But I want to say there does have to be a vertical force here, but I don't think you have to know it. Meaning, I think you can solve this just with a torque balance. But I'm going to guess here and say that this is true. I'll just call it F wall. What else did I want to say? I think that's about it. I think you can just solve this with the torque balance, so you don't have to worry about these forces for the wall, the purple forces. Another reason you don't have to worry about them is because they're at the pivot, right? So forces at the pivot don't exert a torque, and I'm saying that you can just solve this with a sum of the torques equal to 0. And then you should be good. All right, I'm just thinking there, just making sure this looks all right. Okay. Keep in mind that I could have drawn Tx down below T, and if I had, Tx would point through the pivot, right? So I just want to mention that. And they also tell us, I think, that this angle, tell us one of these angles, this angle is 30 degrees. And therefore, this angle right here is 60. And this angle right here is 30. All right. But just realize, I could have drawn the components for T down below, and Tx would go through the pivot and exert no torque. So we don't have to worry about torque coming from Tx. All right. Anyways, that's it. Good luck and have fun with the questions.